let's start this problem with defining what we mean by a prime integer. Now, n is prime, okay, n is prime if 1 times n is the only factorization, okay? Okay, is the only possible factorization. In other words, n has no proper divisors other than 1. So I'll write only factorization. And I've heard it put, you know, just if it has no proper divisors other than 1, then it's prime. There's another way of just saying it linguistically, I think. But we'll just say if 1 times n is the only factorization with a z. Okay. Now we're going to work directly with this definition here of a prime number. N is a prime if and only if this is true. And of course, the difference of 2 cubes is going to come in because that's what we're trying to do. We're trying to find the largest 3-digit prime integer, which is expressible as the difference of 2 cubes. Okay? So this identity, well-known identity, difference of 2 cubes. All right? And of course, a minus b has to equal to 1 because we're talking about positive integers. All these integers will be positive. This part can't be equal to 1. So a minus b equals 1 is a necessary, not sufficient, but a necessary condition. All right, and another way of stating that is a is equal to b plus 1. And we are talking about integers, of course. A is equal to b plus 1. Now, this actually germinated from another problem I was doing that I couldn't solve, so I just used this as sort of the source of that. But I'm just checking some various values, some various integers that differ by 1. 10 minus 9 does differ by 1, okay? And so you would get 10 cubed minus 9 cubed. And you can see how I'm just using this piece right here. This would be 10 squared. This would be 9 times 10, and this would be 9 squared. You see how you get computational value out of this too. You don't actually have to compute 10 cubed and 9 cubed and then do the difference. You can directly use this factorization to minimize the computations. Okay? Now, what we get here, let's see, what does that add up to? 271, I believe. Right, this is 171 plus 100, and this is prime. Now, I'm not going to go through why it's prime. You can check all the prime divisors less than or equal to the square root of this, or less than, I guess. But anyway, that's prime, and I won't bore you with why, but that's definitely a prime number. So that couldn't be the largest one, right? We're trying to find the largest up here. You see, trying to find the largest. All right, so let's bump up a little bit to 15 and 14, which have a difference of 1. That's critical. And so again, we don't have to know what 15 cubed is because of the convenience of this exponent reducing identity. All right, so we get 15 cubed here, we get 15 times 14 here, and we get 14 squared right there. And that comes out to be 631. Once again, we have a prime number. Right, and then that takes a little bit more time to prove this is prime, but it's definitely a prime number. You have to go with the square root of that. You have to check all the primes less than 30, I guess. The square root of 631, something like that, somewhere in there. Okay, now so let's keep going. We're looking for the largest 3-digit one that does it. Now I'm not going to go through each possible case, but it turns out the one that gets it done is 18 minus 17. Okay, let me just write this right here. You would have 18 cubed minus 17 cubed. Okay. Like that. And so you see, again, we're using this reduction thing here. So we have 18 times 18 squared, which is what, 324? Right? Then we have 18 times 17, so you would have to take one of the 18s away. Wouldn't this be plus 306? Okay. Then you have 17 squared, I believe, which is 289. Okay, and then what I got was 919, I believe. 919. Okay, y'all, and I'm just double checking my arithmetic here. 919, which turns out to be prime also. And again, a little bit more work for that. Actually, you didn't have to check. This is the one about the 30, but this is also prime. All of these are primes, and this looks like it might be our candidate because it is 3 digits, right? And it's getting close to the 4-digit range. And it turns out that you don't even have to compute this, but 19 cubed, which is the next one to try, 19 cubed minus 18 cubed is greater than 1,000, okay? I won't do the calculation, not important at all. I was a little remiss about checking these guys for primes, but they are primes. This is a prime, this is a prime, and this would be the answer to our question, 919. And it is prime. It's the difference of 2 cubes. And this is our very next attempt is already greater than 1,000. Okay, so that proves that 919 is the answer to the question. Thought it was kind of a fun question. I started out trying to do something a little harder, and then I discovered this necessary condition here. And I don't know if there's any other interesting problems that you can get out of this. You know, I was looking for necessary and sufficient conditions for, the difference, prime number being the difference of 2 cubes. I just found a necessary condition here, But anyway, I did get a problem to work, and that the answer to the question here would be 919. 3 digits, and it's a prime number. As the world turns.